I have many of the slides that you've seen up front, but I intend to go through them very rapidly. We are a smaller session. I don't think there's only 3 of us for 2 hours. So I think for the most part, we should treat this as something of a, if you have questions, launch in. I mean, the object, it was, and I'm going to give, it has nothing to do with the talk. The object was to put together, sort of a group discussion just to look at the use of isotopes, because it seems that they're very useful in a lot of areas, and metabolomics up until recently has not seriously used them. And what's sort of fascinating, if you look at the course of the day and yesterday, we've actually seen quite a few instances where isotopes are coming into play, and they're really, I think, what Professor Schumacher has shown, what we've seen in so many places now. I think they're really going to change metabolomics, and so that's the tactic I'm taking. I'm going to talk about one of the techniques, and it's one that is a personal favorite, but that doesn't mean it's any better. It just happens to be one that I've thought a lot about. So it's IROA. I discussed it very quickly yesterday, and the key to IROA is really this concept that you use isotopic balance to encode information about the molecule, specifically the number of carbons and the exact mass, into the mass spec, and then you can use that information at a later time. And it's all based on the fact that if you know the number of carbons and the exact mass of a peak, it's very hard to get the formula wrong, especially below a mass of 450, but even up to masses of 1,000, you just have a much better handle on everything. So it's information policy. Normal mass has there's with a natural abundance, you have a little bit of a peak for an M+1, but by moving to a different isotopic balance, you create a very strong M+1. That M+1 is the kind of information I'm talking about, and of course the obvious thing is that the little M+1 is moving to the positive mass direction. The same thing occurs if you started with a pure C13 isotope and dope in C12. Of course, that mass is going to be smaller, and if you are talking about a random, uniformly distributed population, which is the key to the entire thing, then in fact you get this perfect pattern that trails off down in the negative direction. And so you have 2 populations that you can view against one another, and that is the information content that we're really talking about using, and I think lots of us are talking about using very similar forms of this information content. It's easy to put into cellular-based analyses, and then using the same concepts that we have in the proteomics world, pooling samples. You start pooling these samples, and thereby, once you've pooled the samples, you increase the data accuracy by removing sample-to-sample variance, because all of your sample prep, all of the variance introduced during sample prep and the variance introduced during the analytical process is now immediately subjected to both the control and the experimental. So your comparisons and your normalization, your post-processing steps are equally doable. So it ends up giving you a significant edge because the patterns are so mathematically based. It's relatively straightforward to write routines that computer routines that can go through scans. I'll say, speaking of our, the software that we wrote, we're processing a, 20-minute mass spec data set in under a minute. And, doing it, just, I mean, the computers are now very fast. And I don't think we miss much. I just don't think it can. The patterns are just so strong. So there's a 5-carbon molecule, a 6-carbon molecule, 7-carbon molecules. The patterns are all different. They may be subtly different. They may all look the same to you at first, but once you get used to looking at them, they're not the same at all. They change depending on the number of carbons, the relative heights, and the percents. So every molecule now carries both the experimental and the control. It carries within each paired peak actually the formula, because the number of carbons, if you're dealing with any form of exact mass, and exact mass is even less than 10 ppm, and these days that's not hard to achieve. You actually have an unambiguous hold on formula for every given molecule, and it's just very, very straightforward once you migrate to it. You can't always label everything, and so one of the things we've been talking about over the last day or so is the use of this as just using the information content in the 95% channel. I tend to refer them to them as a 12% channel and a 13% and the C13 channel, just to allow me to identify its natural abundance pairs. This is where you're using the C13 material as an internal standard, and as an internal standard, if your C13 material is biologically related, and has a roughly similar biochemical makeup, then it becomes a targeted analysis in which you can, identify a huge, a large number of compounds, and you measure relative to your internal standard, and it gives you, very easy access to highly qualified data. And again, you've removed all of your sample-to-sample variance. You've removed your analytical variance. So you're talking about pretty reasonable numbers. And so this is the phenotypic mode. And the pattern, it looks different in the real world, but in point of fact, it's absolutely predictable once you get it. So there's the two ways. If you can label both channels, the C12 and the C13, then you're talking about an unbiased analysis in which you can find any and every compound that is produced or absent from, your experimental, in either the control or the experimental, or your phenotypic, which is a highly targeted analysis. I'm going to, again, these peaks, they're mathematically precise. They follow a well, defined set of rules. And so it's very easy to figure out what they are. They're the binomial distribution. As I said at the outset, I'm going to move through this sort of quickly because I think you know it. So it normally, the masses, the m+1, would be a polynomial distribution, but because carbon at 5% is so dominant, the others, basically fall by the wayside, and the binomial distribution gives you gives you an accuracy that's probably better than most mass specs on the market today. And it's no sneer on any of the mass specs. The technology is amazing, but 5% is just so much more dominant than the other isotope abundances that it blows them away. Ion suppression is just a form of analytical variance, and of course, it's removed. Compound identification, as I've said now, if you have an exact mass on either of the monoisotopic peaks, and you always do, and the number of carbons in the molecule, then the formula is generally a given. You can rarely get it wrong. And that's, shown in this slide by, if you, at any given mass, if you, produce the mass and calculate the number of potential formula that could fit it, shown in red, and then you say, but if I know that it is X, if I know that it's 5, I know that it's 10, I know that it's 15, the number of formulas that comes back is just dramatically smaller. So you've really helped in your identification a lot. The normalization routine, is simply the same normalization routine you use whenever you use an internal standard. The only difference is that in this particular case, with this sort of a protocol, you have a complex internal standard, and so you can in fact use the total area under the curve for the entire standard and use that as a normalization point. And I find that there are situations where it works great. And then there are situations where, I'll show you some toxicology experiments. There is real science coming. But, in an area where you're, grossly affecting cellular growth, like in a toxin, the cancer chemotherapeutic agent, on tumor cells, you may not want to normalize the data. Normalization may be the last thing you want, and so, you have to be careful and think about the nature of the experiment when you do any of your post-sample data preparation. But the normalization is always available to you, and it's a fairly high-level normalization because you're only using data points that are coming from a well-defined 95% channel. This is now we're at the level of a personal peeve. I have always believed that the Z score, the Z is one of the best of the normalization routines. This is where you characterize completely your control population and you look at your experimental population relative to your control. Observed minus mean divided by standard deviation. And this is very simple math, always applicable. I understand that everybody has a different method, but I personally, I think the doctors stand behind this every time they measure your cholesterol. But for some reason, most experimenters don't want to use it. They want to do, standard deviation 1 minus standard deviation 2, or, some complex. They want to use, the mean and standard distribution of the entire population, experimental and control, which of course simply dilutes your values. So this is old-fashioned. I'm going to skip all of this stuff because I did it yesterday. So now to the science. So I really did want to show you today how you can use it. And we've got, so this was a study done at the University of Florida, recently published in Analytical Chemistry, and I forgot to put on the slide the reference, but I'll be happy to give it to you. C. elegans is, of course, otherwise known as the worm. Total of 959 cells, has a very rapid growth, so you can go from, egg to egg in, I think it's a 2-day period. It's, remarkably fast. They feed on bacteria, and since bacteria are so easy to label, it's very easy to label worms, and their chemistry is fascinating. Despite the fact that they have mouths, they obviously don't talk. So all of their communication is chemical communication. And so in addition to looking at their metabolism, one of the other beauties of this experiment was the fact that just in harvesting the media and looking at the media, you could see all of these ascaricides that they had produced. And again, one condition relative to another condition, how the communication differed depending on the environment. So, you know, the worms were a great model. Oh, there it is, 3.5 day. They're easy to handle, and we've got lots of experiments now, you know, going on based on these worms. So they were treated with hydroxyphenanthazine, otherwise known as 1-HP, and this is a toxin for the worms normally produced by Pseudomonas, but it was, you know, purified and chemically available, and so they wanted to treat it with this toxin. We've also treated worms with a lot of other stressors, but experimental protocol looks exactly like what you now know and love. You know, you grow up the worms on one of the 2 bacteria foods, and once they've become labeled, you perturb them. In this case, adding HP1, and then after the appropriate amount of time for them to respond to HP1, you collect the cells and you pool them with the control, the treated only with vehicle, and measure them in the LCMS, and then measure, in this case, I always recommend because there can be isotopic effects in metabolism, and it actually doesn't hurt the experiment as long as you recognize them and accommodate them, which is, again, mathematically doable. Anyway, because of that, you always want your internal standard to be the 95% channel. If you make your 95% the control, then if there is an error, an isotopic error in metabolism, you really haven't affected anything, because it just means that your experimental control, the untreated experimental, is going to tell you that there was in fact an isotopic balance, and that's how you determine that it was there, and that's how you mathematically accommodate for it. Experimental design is another thing that this allows you to. I don't know. I love experimental design. So anyway, we found 742 very strong IROA peaks. We didn't bother going after the weak ones, and I'm going to show you basic statistics, principal components. I'm not a big fan of principal components. I'll show you NMF and random forest, which I am a big fan of, but everybody wants principal components, so I'll show it. I'd love a question as to why we shouldn't be using it, but maybe I'll discuss it. 74 compounds were considered significant, and so the basic statistics we generated by in a very straightforward fashion, and very strong statistics. I mean, no big deal. We're treating these worms with a toxin. If you didn't see a very strong response, you'd be amazed. And so, if I look at the statistics, and I only filter out, I'm going to, and I'll do this a lot because I actually think it's a very significant point. If you run a correlation plot of a correlation matrix of the most significant compounds, and I will do this to most of my data sets. This one is not particularly informative because it is telling me effectively what I already know. I have two very strong populations here, right? So the other thing that is, and we saw this in some of the talks earlier, we have a tendency to think of biomarkers as single compounds. The fact of the matter is, these biological responses, yes, it was your talk that made this so clear. Biomarkers, we happen to select one compound, but here are two groups of compounds. Any one of the red compounds would be a biomarker for the control blues. Any one of the blues would not be a very good candidate because in this particular test, all of those compounds are highly correlated to one another. But I'm making that point now because we are going to see this as I move into these correlation patterns again and again and again. You'll see the strength of these patterns, and I think we need to learn how to deal with this. Is a very good way, I think, to look at our metabolomic data. So anyway, very simple here, but it gets more complicated. I love random forest. I think random forest is a very good technique. Random forest is supervised. It does know what the samples are, but it's a very good way of understanding what the most important compounds are. And so I always run a random forest, and no big surprise, it gave me a very clean separation, and allowed me to find again the most significant compounds. Surprisingly enough, the most significant compounds found by random forest and found by basic statistics are not always the same. The top compounds in one are not always the other. The implications of each of these statistical formats that I will show you, they all have different assumptions, and you should never assume that you can run one test and use the information you get off that one test relative to the other. You always want to think about what are the underlying assumptions. So anyway, I love random forest. I think it's a very good way of looking at a data set in the entirety. This is the technique that I would put in place of principal components, is non-negative matrix factorization. If you think about what a principal components is, in a principal components you are actually trying to squash all of the variance that is in a data set into as few components as possible. Where in the real world would you actually want to do that? What you really want is you want to find all of the correlated variance and then put each of the correlation sets into its own level and understand what those levels are, because each of those levels has a very good probability of being a subsystem that is relevant to the experiment that you're looking at. People hope that you can do that with principal components, and it will give you a separation. But NMF, on a more complex experiment, will give you a much deeper understanding of what's going on. And so I would urge you to think about it. We just published this is another pet peeve. We just published a paper in American Statistician just to get the statistical community thinking about this technique, because it's fairly new math. NMF only began to be successful. It's computationally more intensive, but it became a successful technique in the late 90s. But it's a much better way of analyzing data. I promised you a principal components, having given you the talk. Needless to say, it gave me a very good separation, which it has to do. I mean, it's not a bad technique. It just, you don't get as much information out of it as you want. I'm a believer in self-organizing maps, and so I always generate, self-organizing maps. And here they're fairly trivial, because here it's simply saying that there are in fact two gross patterns, it's identifying and characterizing the various, players in each of those levels. So if I looked at all of the results, again, what I said a second ago, you need to understand the underlying assumptions in each of those techniques. They're all different. And so what I love to do is, since I run them all on a regular basis, I wouldn't not do it. I then see who is statistic in, who is significant in all, in the greatest number of all of the techniques, to remove, as much of the influence, the underlying assumptions as I can, and come to some sort of consensus as to the significant players. And so, I think that is a next good step in, a metabolomic analysis. And, and then if I look at the compounds that are, found for, after having done that analysis, I invariably am left with a data set that, these are the compounds, and this is what they look like. And they're, they're generally all, highly qualified. And so then there's having done that, you can then map them onto a standard biochemical map, and see if you can deduce anything beyond that. And I think there's other techniques beyond that, but that's the standard. Yeah. Yeah.
Basically, you can split it into two blocks.
Yes.
All the methods you show is split it into two groups, and by kind of picking and choosing which one you want to look at.
Absolutely.
It's a slippery slope, right? It's deciding how you're going to analyze it after you do the experiment. But you really want to decide how you analyze it before you do the experiment, so that you avoid making the story, right? Because people are really good at making up stories to explain data.
Absolutely. So let me just. So I am walking you through the worm study because it was just recently published. In a second, I'm going to move to a situation in which I have done the same thing, and there's a flaw in the second study. But in the second study, I have 3 different toxins, and I will demonstrate that the overall patterns of toxicity are different within the 3. And so I do agree with you that on some level it is, I could use any one of those compounds as a biomarker.
Right.
Bottom line. So if all I'm looking for, you don't need to do any of this to find a biomarker. But if I am sitting there trying to say that this is a technique that helps me get at metabolism, then I first needed to walk you through this and demonstrate that you can get a reasonably complete data set that is, I think, strong statistically. I needed to walk you through the math because I'm going to do it again. But I also, the end point of all of that is that I have profiles for these toxins, and the profiles are different from toxin to toxin. So I appreciate what you're saying, that in this particular case, for the worm, it's overkill. You don't need it. But anyway, so the bottom line is I can give you a rough mechanism by showing a superposition of who is up and who is down. And theoretically, I could get a mechanism of action if I had enough data points on this. I'm only showing the statistically significant ones as up or down, and everything else is all the bigger grade ones were seen, but not statistically significant. You can go through fold changes for specific compounds, and this point's anyway. Here's the study now where. So I then sat down and wanted to do another one that was more complex, that would allow me to actually say, can we tease out more information about mechanism of action and do, so basically we treated yeast with 3 drugs, control, flucytosine, ketoconazole, and terbinafine. For those of you in the audience that do not know, flucytosine is an inhibitor of DNA and RNA biosynthesis. It inhibits cytosine nucleotide production in general. Ketoconazole and terbinafine are inhibitors of cholesterol metabolism. So you have 2 drugs with a similar mechanism of action and 1 drug with a very different mechanism of action, both of which kill a fungus. And the 2 similar mechanisms of action are actually attacking different sites. So in the cholesterol biosynthesis, ketoconazole is, I think, the last part. The demethylation, and the terbinafine is, I think, very early in the biosynthesis. In this case, again, we didn't mine very deep. We found 499 IROA peaks, as is 100 of them were named, and only 100. Again, basically no strong response. I'll tell you the problem with this study was, and this is not yet published, but I don't mind showing it because it's never going to get published. I'm going to redo it. The concentrations of the drugs were calculated to be too high, and I'll show you that at the end, and you'll see it and you'll understand it. Anyway, I hadn't shown you an image like this before, and since this was an older study, I did think it was worth showing you what the C12 and C13 peaks look like when they're superimposed on one another. The top two rows are compounds that are not affected, and so effectively the C12 and the C13, there are two colors in each one of those peaks, and sometimes you have to look, but there are two colors for each one of those in the top row, and then the bottom row, those are all nucleotides, part of nucleotide metabolism, and you can clearly see, that the biosynthesis of the metabolic pools of those compounds were clearly very strongly affected. The basic stats, we're talking about 3 drugs, so we still see, for basic statistics, we're still seeing 2 strong patterns and a series of interacting patterns. The patterns for D, E, and F are the individual drug patterns. The pattern for box A is the overall response, and this is where I began to realize that the problem was I was really looking at death. This dose was too high. The 3 doses were higher than I wished. But again, very strong statistics. It's clearly seeing differences. The 3 drugs are grouping based on the total data set. Quite easily, bless you. This is a principal components of a self-organizing map. Again, my random forest. Random forest effectively gives me a perfect separation of the 3 drugs, the 3, from control. It's giving me a very good list of important compounds in addition to the statistically significant compounds. I move it into non-negative matrix factorization. I have 3 drugs here, so I'm accepting the level 4 K equals 4 NMF. There were also K equals 8, K equals higher than 8, but they're too complex to discuss here. But this is a very clean separation. If I look at each one of these levels, I now have, not only does each one of these factors give me a clean identification of each group of samples, but for each one of those, and I've given you if I run a regression on the analysis, I'm getting a value of 9 times 10 to the 5th. So it's giving me a very clean separation of the samples based on what it's able to pick up as highly parallel responses. Yeah, I'm sorry.
What was the indication that the drug was too high? Just because you removed
I think it's because I'm really looking at death. It's because in the what?
Is it just because there are too many changes?
No, it's because there are too many changes that were constant. So I think that I would personally, my intention is to run it. Great question. Because I suspect what I'm really looking for is, I think what I'm really looking for is the responses that are close to the limit, the minimal dose. And I fed a regular dose. So we calculated the regular dose down. And so my guess is that what I'm really looking at is the cell shutting down. And so that's why I think what's happening is I'm getting such a strong two-pair set of responses across the entire data set. I think I'm just looking at the cells shutting down. And so what I'm looking at here is, and so I've got a signal, because the patterns for each of the drugs is telling me that there is another signal in there, that is, drug by drug effective. But I think I need to redo the experiment at, closer to the minimal dose. Anyway, that's just my being, that's what yeah, I'm being honest. I think it's not an experiment that I will publish, but it's one that I think was successful enough that I think it's worth showing for these purposes. I should point out that the two drugs these are your two cholesterol lowering drugs, and so they are sharing a certain number of responses, but one of them has a lot of additional features. There's my flucytosine, there's my control. So, each of the levels that is coming through the NMF is giving me a series of compounds that are highly responsive for each one of those populations. And there are the profiles that I'm getting. And if you look at the individual colors, for the most part, you have, fairly strong responses. That are highly differentiated, and in no case is everybody low or is everybody high. Sometimes the reds are low, sometimes the reds are high. But so, where are the significant compounds for? Again, overall, we're seeing a shutdown in nucleotide biosynthesis. Green is it's gone down. The levels, the overall metabolic pools in all of the cases, the experimental cases, has gone down, and that's nucleotide biosynthesis. It's a strong driver. They're all shut down, and we do see other metabolic pools that are being strongly upregulated in all of these. This is why I say that I think that I'm really looking at death. That if I look at the overall response for all of the compounds I measured, so I simply linearize the response, whether it is up or down, there's just too much similarity between these. And, even though there are differences, there's no question. You can find, you can discriminate mechanism of action within these profiles. But I think I'm looking at a lot of additional response. This is yeast. Cerevisiae, yes.
That's known to have what a defined stress response when you hit them with a bunch of different stress responses. And they've even got the generalized stress response.
No, I didn't know.
Yes,
you have to understand, I'm a chemist. I'm a mass spectroscopist, really. I beg people to do these things for me. I will tell you that, you look at this region, it's very different. Terbinafine, flucytosine is my nucleotide reducer. There are portions of this that are different. So I think that they're within the stress response.
well, it's called I believe, if I remember correctly, it's called environmental stress response. And I believe it's about 800 genes that are
I would hope that I could get the dose down to,
Yeah.
low enough that I would actually see just the response from the drug.
And I agree.
Yeah. I mean, if I'm stressing them too much, can I go down to a level that do me a favor. I had another. I think you've had a question for a while.
No, it's rather a comment because we did some similar experiments with herbicides on plants.
Yeah.
And we encountered the same problem, of course, that they died from the drug applied,
Yeah.
which you don't want. And we had really a hard time to find a dose where you could see the effect which we want to see also. And we had exactly the same effect as what you said. If you have a general abiotic stress effect, which you could mimic to some part by stress or salt stress or acidic acid, but only to some extent, because there is also different responses to the different stresses, of course, and there's a general response. And just lowering the dose was not enough, but we had to really have a dose study before
Yeah.
starting this to find out what is a reasonable one. And still then the results were, well, they are not published yet either.
Yeah. Okay. But I
Difficult. It's very difficult if you have a lethal compound as an inducer. So
years ago I did, and then I will take your question. I haven't. Years ago we did do a study in which, this was in my days at Metabolon. We did do a study where we were looking at a series of doses, and I recognized that below the minimum lethal dose, we were able to detect the cell responding to, the point of the drug's attack. And so I think that if we can get the dose down to, minimum detectable, then, and maybe even half that, we should be able to see, the kinetics of the enzyme that's being attacked changed. And so that's really my hope, is to go really, really low. But I'll take your point that you couldn't get there.
but still you cannot predict really because in some cases the responses were such that they brought up exactly that metabolism which would then supplement for the inhibited part.
Yeah.
In others you would have some general regulation of metabolism. So this was really, of course, then you see different patterns for the different herbicides in our case,
Mm-hmm.
biocides, whatever you would in general. But the problem is that these patterns don't tell you anything. I mean, our hope was, of course, to find something out about the mechanism of these herbicides. And in one herbicide, and we tested that, of course, with known ones. And in one case, okay, one could deduce something, like it was redelivering a lot of these compounds which biosynthesis was inhibited by another pathway and so on. But in other cases, it was totally non-related.
Yeah.
And so the question is, whatever you see a pattern which you
Well,
might be able to identify it, but what is the meaning of this pattern?
the,
That's the problem.
it is the problem. But I guess I'm hoping that if we get a profile, that if one was to do this on enough drugs, then you could find the common features of the profile that, to be perfectly honest, most herbicides and most toxins are never screened for their having secondary effects. So there's no reason in the world why you should expect a toxin to have a single locus of action. So in a sense, this is the hardest of all cases to make. But on the other hand, it's a place to go. And your question.
Yeah, so again, I'm kind of I'm a chemist by training like yourself, Chris.
Right.
But I got experimental design training early on.
Right.
I transitioned to the dark side of IT and informatics. so I look at this data, and so in last study you had a treatment and a control.
Right.
So you had one bit of information. Here you have three drugs, or
Right.
three toxic compounds,
Right.
for control. So basically, the only
theoretically don't. I mean, you're right. I mean, one could add a timeline, and that would give you part of the kinetics that you might be looking at, and that would give you differentiation. The other thing that you could do is, I think that all of the compounds are responding differently. I just don't know how to. I mean, so the trick is to really, take the next step, is to not just find the significant ones, but to tie them all together. At the moment, that's still a slippery slope.
Well, so the challenge, right, is with a single point, you can't tell very much.
Right.
That's why
Yeah.
you need to do time courses of perturbation.
Right.
Think about how they do ultrasounds, or they look at ultrasonic mapping of the ground. They take lots of findings, and then they look over time, and then you get a lot more information. So then you can look at how the pathways change over time.
Right. I'm going to take one more question, and then I'm going to abandon this because there are two other people to talk to, and I've got they have maybe more interesting stories. One more question. Mm-hmm.
Once you come to the steady state, or as you get closer to a steady state, it's harder to differentiate two groups. But if you're in some sort of linear, pseudo-linear, then at one point, somewhat reasonable. But you got to do your homework in advance to know something about the time course.
Yeah. Well, I think I did not do enough homework here. I think these doses are too high. I think that if I could get to a lower dose and maybe throw in a time point, a time curve, but. I mean, they're still clearly differentiating one another. And I'm going to stop. The worm work was done at the University of Florida by Rick Yost and Art Edison and their groups. The work on the yeast was done at the University of Michigan, and I have had hope, strong help from both Thermo and Agilent in looking at this, and thank you very much. And I'm not going to take questions, not because I'm afraid of them, catch me later, but because I think other people need to talk.
Okay. Thank you, Dr. Beecher.